Hello, everyone. My name is Andi Braimllari. I'm an alumni from the Technical University of Munich, Germany. During my master's thesis at the university, I worked on a project titled Hybrid Reconstruction using Shearlets and deep learning for sparse X-ray computed tomography. We have achieved some interesting results that, I'm thrilled to share here with you today. So, what is this hybrid technique about? Its focal point is to improve the reconstruction of sparse CTs. How it does that is that it utilizes Shearlets in order to split the signal into visible and invisible parts, and then utilize model-based techniques to reconstruct the visible parts, and then deep learning model PhantomNet to in-paint the invisible parts. Afterwards, it brings everything back to the spatial domain through the inverse Shearlet transform, which we can see in this diagram. As a brief aside, sparse view CT, we can see through the blue nodes that these parts are actually the invisible parts, but we'll get a closer look at this in a bit. All right, so the outline of this presentation is as follows. We will be diving a bit deeper into the separate components, which in this scenario are the Shearlet transform, the sparse localization, as well as the deep learning model, which is the PhantomNet. At the end, we'll have a look at some experiments that we have conducted, and then provide a brief summary for the whole thing. Right, so what are Shearlets? Shearlets are a powerful mathematical tool initially presented around 2006, which are central to our hybrid technique. They are able to split the edge information of the signals, which in our scenario are the scans, into visible and invisible coefficients. They can be constructed through three operations, which is a parabolic scaling, the shearing itself, as well as translation to a single chosen generating function, which has to be nice enough. Let's put it that way. This, of course, defines the Shearlet transform, which takes a signal, which say it can be a 512 by 512 scan. It transforms this to a 59 by 512 by 512. 59 is considered as the oversampling factor, and this can be handpicked, and it can be decided also by the actual Shearlet systems that you have implemented. One very important thing to note is that Shearlets provide an optimally sparse representation, and they enable efficient encoding of anisotropic features in multivariate problems, which is our scenario. On the right side, we will see the frequency tiling of cone-adapted Shearlet systems, which is what we will be using. The alternative would be classical Shearlet systems. We will not be using that because they exhibit a bias toward the vertical axis, which means that functions whose Fourier transform would be concentrated around this vertical axis would be almost impossible to represent using such classical Shearlet systems. So we'll be sticking with this, and we will be using the Shearlet transform that comes out of this one. Right, so how does it actually look like? As we said, Shearlets are capable of encoding the boundary information of the given signals. Well, on the left, we see an actual human abdomen CT slice. So we have a 512 by 512 image. And after we apply the Shearlet transform to it, we can get a 59 by 512 by 512. And the middle image is one of the earlier subsets of this stack. We can see that it somehow visualizes a general overview or a top layer of the actual scans, while on the right side we will see a much more finer or granular subset of the actual initial CT slice. one analogy that I like to make, which might help visualize what the Shearlet transform is actually doing. You can picture the convolutional neural network, which after it has finished training, and you have a look at the feature maps, you see that some of them tend to learn or encode information regarding the general objects that have been provided in the training images, while some feature maps tend to learn some intrinsic small primitive patterns, for example, half a circle or a straight line or such patterns. This is a similar scenario for the Shearlet transform its output. All right, so tomographic reconstruction with Shearlet sparsity, we simply see the traditional optimization problem with the data term including the radon transform along with the noise, and of course the weighted Shearlet-based regularization term. We see the constraint here for the signals to be positive. It could also, you could have it or you could not have it, but it has been demonstrated that it improves results. And of course, particularization, it operates on the assumption that the output of a problem can be described by a fewer number of inputs, and we will be using the alternating direction method of multipliers to tackle the aforementioned optimization problem. All right, what is the actual deep learning model that we'll be using? So this whole approach is based on the learning, the invisible paper, and we will be using this model. One very important thing to note is that PhantomNet, codename PN, operates in the Shearlet domain. So the input to PhantomNet will be the output of Shearlet transform to the signals that we will be using. This is a traditional unit, multi-channel input, multi-channel output, which of course it has the encoder part, the latent space, which encodes the relevant information, and of course the decoder part, which then outputs the in-painted invisible information as we discussed initially in the diagram. One thing to note regarding this architecture is that it uses trimmed dense blocks, which are a flavor or a version of dense blocks. Well, what are dense blocks? They were published, if I recall correctly, by Cornell and Facebook AI research. They represent groups of layers which are highly interconnected. So the input to the upcoming layer would also take into account the outputs of all of the previous layers. Yeah. So here we see in detail the entire diagram of the hybrid reconstruction for sparse CT. We begin with the measurements in our scenario sinogram, and after we apply the ADMM to the optimization problem that we just saw, we have the reconstruction. Up until this point, we have a reconstruction, which can be a 512 by 512, and then we apply the Shearlet transform to it, which can be, say, 59 by 512 by 512. And into a trained PhantomNet, we can perform inference on it, which will give us the in-painted invisible coefficients. We can then summarize them with the actual reconstructions. And at this point, we have the reconstructed visible coefficients along with the in-painted invisible coefficients. To take the whole thing back to the spatial domain, we apply the inverse Shearlet transform, and we get the hybrid reconstruction. All right, so for a more rigorous depiction of the outline, yeah, we have the optimization problem that we just mentioned, which allows us to retrieve these visible coefficients. And then we train the actual PhantomNet. And at the end, we simply combine these visible and invisible coefficients. Yeah, please note that there are these inv and vis for invisible and invisible masks. The invisible masks for the output of the first step is approximately 0 because this represents the invisible parts, evidently, and to retrieve that, we have the approximation with the inference that the trained phantom net does. So the final formula that you see at the bottom represents the actual reconstruction, which takes into account these two components. Right, so regarding experiments, we use a data set that I've seen used quite a few times in this conference. The low-dose CT Grand Challenge, the data provided by the Mayo Clinic. It contains human abdomen scans with width and height of 512. We handpicked 10 patients and used the scans of those, which constituted 1,525 images, and we used one patient only for testing, which consisted of 96 images. I want to emphasize that the sinograms that we have used have been simulated by 64 projection views over an arc of 360 degrees. The 8mm, which we just mentioned, we used 10 iterations. You could use more here, but time was of the essence for us. And then we use 5 iterations per ADMM, which we utilize conjugate gradient, and row 1, row 2, and the weight of the regularization term, those are handpicked. The proximal operator for ADMM was self-thresholding. Regarding the training of the deep learning model, we have the learning rate and the weight decay. We trained it for 100 epochs with Adam on a loss of mean squared error. And on the right side, we can also see that the loss graph seems to be substantially going down even after 60 epochs or so. We trained it for about 24 hours on an A100 with a batch size of 1. That worked fine for us. So regarding seeing these outputs, on the left side, we see a ground truth of a human abdomen scan. On the middle, we see an ADMM reconstruction, which in our scenario is also the output of the first step of the hybrid method. And on the right side, we see the actual hybrid reconstruction of, which is the entire thing. If we have a look at these zoomed in parts, we see that data, the features of the signal seem to be much more preserved, or should I say well reconstructed in figure 7 when we compare it to that of the ADMM reconstruction. We've also computed various metrics to support these visual claims. So relative error, peak signal to noise ratio, structural similarity index, and Haar wavelet based perceptual similarity index. The lower the RE, the better. The higher the rest, the better. And the hybrid reconstruction does in fact outperform the reconstruction of ADMM. One thing to note here is that regardless that the zoomed in part does seem better than ADMM, we can see that some features seem to be slightly smoothed out. And this is an effect that we noticed during training. So this does not come off as a surprise. If we see on the left side, the reconstruction from a poorly tuned phantom net, we see these streaks, as well as certain features that tend to be smoothed out. But if we train the deep learning part with more images, and if we train it for longer, and we properly tune these hyperparameters, we can get something that looks like more on the right, which does not seem to suffer from this smoothing out of features. We also computed the metrics again. Of course, on the right side is better. All right. So to summarize, this technique has been fundamentally based on the Learning the Invisible paper, which used it for a limited angle scenario and we see it used here for sparsity. Yeah, something very important. The code for this is open source. You can find it in the ELSA project, which we will get to in a second. And yeah, I guess that's it. I'd like to bring to your attention the ELSA project, which you can see at the bottom right. If there's anything regarding the code that you'd like us to further clarify, or if you want to simply have a look at it, please do. You can see the contacts for the 3 authors, as well as the address for the CIP department of the Technical University of Munich. This concludes the brief talk. I'd like to thank the supervisor of this project, Tobias, and of course, all of you for your attention. I'd be happy to take your questions.
Yes, talk is open for questions.
Hi, Andi, thanks for your talk. I was wondering, like, after the Shearlet transform, you have like a stack of images in which you have like this general blurry version of your slice with then this fine detail stuff. And you told us that you had a stack of 59 images. I was wondering if is the size of the stack variable, and how does this affect the results?
Correct. It is variable, and it depends on the scale that you choose. If you want to have a more precise answer, it depends partially by the frequency tiling, because in order to generate these layers or subsets, you're going to go over through the tiles of this this figure, and so yeah, the number will depend partially on how many tiles you'll want, among other things. So yeah, to get back to your question, it is variable. And another Shearlet transform that I implemented, that one produced 61. This one here produces 59 subsets. So yeah, it is variable.
Yeah, and is it like automatically generated, or can you tune it yourself, or is there like so it's a nice way to choose how many or how large the stack is? Or
so it's a formula that depends on these parameters of the Shearlet system. So A, it represents the parabolic scaling, S represents the shearing, and T the translation, and the formula that determines that takes into account these parameters, among other things. So yeah, there's a formula for it.
Okay, thank you.
So you can just handpick it, like 3 or so. It has to be related to the actual Shearlet systems.
Okay, thanks.
Thank you.
Yeah, thank you for the good talk. What I am curious about, why I've seen similar approaches in literature before, and sort of what's the general opinion of why the network needs help sort of deciding what to look at and what not to look at? I mean, ideally, the network would learn that certain spatial frequencies were the most important, and it would just address those and conserve everything else. So, what's your opinion on that?
Yeah, that's a good question, and that actually cuts right into the core of this topic. So the thing is that initially this method comes off with like an appendix of the best of both worlds, which is how often this hybrid method is done. And one reason for that is that if you are going to have if you're going to do inference or training through deep learning of certain signals, you might get very good results during a phase, for example, training, but then you won't be certain in regards to how much your model will change the signal, for example, in production. So you'll give it an input in the spatial domain, so a slice, but you won't be extremely certain how much that will change in the end. As to when you compare it to a model that works in the Shearlet domain, this model actually learns these intricate edge patterns or boundary information of the slices. So, for example, these are maybe the one on the right, maybe a better example. These tiny patterns and things like that is what the model will learn, and not something like the actual slides, which might be, say, contaminated by noise, different features, different parts that aren't really related to the actual slice. So that is one huge advantage why working in the Shearlet domain rather than on the spatial domain. So you have these things that it can actually learn that pertain to the signal and not just features that we see from the signal.
I think another component of it is related to, similar to residual networks, where they work on differences instead of the low spatial frequencies. Essentially can't bias the low spatial frequencies if you don't actually put them into the network. So I think that has a lot of benefit as well. Zero centering everything by looking at high frequencies.
Yeah, that's a great question. There are many aspects and many ways to answer that. So yeah, I hope I provided a decent one. Thank you for your question.
Okay, so if no more questions, when we can conclude this sessions, I'll give you one more.